All right, we can start now.
Yes.
Okay. All right. Assalamualaikum warahmatullahi wabarakatuh. To ladies and gentlemen, good very evening. Today we continue online global classroom with Dr. Fiza Raza. All right. Before that, let's scan the attendance for e-certificate and voting at the menti.com. Okay, the code 2113002, or you can go to the link as the following. Don't forget, okay, you also given the link for the attendance and e-certificate after this session. All right, welcome to Dr. Fiza. How are you, Doctor?
I'm doing fine. Thank you so much. How are you?
Fine, Doctor. Okay, how the university, Pakistan, okay, the population there, right? Your colleague about the COVID-19 pandemic in your region.
Yes, as you know, there is second, and so in most of the parts of the world, there is third wave. So the campuses are closed for on-campus teaching, but we are working online as usual, and we are taking the classes and the exams. So we are trying to cope up with all the problems that we are having, and we want to deliver the students our best in every way.
Oh,
So everyone is trying, every teacher is trying, every researcher is trying to handle the situation.
so how the implementation of the education 4.0, or we call as a future ready education?
Yeah, there are learning management systems in practice in most of the universities, whether they are public or private universities, and the interactive modes of learnings are adopted. Uh, the problem is only with the research in the labs. So, but we have some restricted facilitation for the students to go to the labs whenever they require, because there are many MS and PhD students who are working, and they need to find out their findings, experimentations regularly. So limited entry is provided to them. But for the other teaching case, we are going for the education for learning management systems, interactive learning modes, the interactions through which we can have the feedbacks of the students, and then we can keep on trying to adjust accordingly to improve our teaching methodologies.
Oh, thank you very much. Very detailed explanation about the education 4.0 or future ready education. All right, so now let's introduce, okay, Dr. Fiza. Right, you can see here, okay, the information about Dr. Fiza. Okay, Dr. Fiza Zafar from Baharudin Zakaria University, Multan, Pakistan. All right, so she is tenured associate professor in mathematics. All right, and today she are going to deliver the topic on iterative methods for solving nonlinear equations, application, and dynamic analysis. Okay, Dr. Fiza, okay,
Yes,
PhD and postdoctorate in mathematics. Okay, if not mistaken, your postdoctorate in Europe country. Which country, Dr. Fiza?
yes, in Spain, in Spain.
All right, very. I think it's very intensive experience. Okay, in
Yeah.
the overseas, am I right, doing the postdoc, and then expert in the numerical analysis, research focus on numerical integration, numerical solution, and for the nonlinear equation. All right. So she is now in the Department of Advanced Studies in Pure and Applied Mathematics at the Baharudin Zakaria University, Multan. All right, so let's we go for the abstract. Okay, this is an abstract which we are going to focus is more on the application of the nonlinear equation. I saw here you are using some numerical method, for example, Newton iterative method. All right, and then visual using some numerical software. All right. So
Yes.
without any delay, all right, let's we share screen for your talk today, and this broadcast is for you now. All right. Welcome, Dr. Fiza.
Thank you very much, Dr. Norma. Thank you for the nice introduction. And I also like to thank University Technology Malaysia and Dr. Norma Ilyas for inviting me to present this talk and to be a part of online global classroom of University Technology Malaysia. The topic of my talk is iterative methods for solving nonlinear equations, their applications, and dynamical analysis. From the title, it may seem that it's going to be a conventional mathematical talk in which we will be having a fundamental problem of root finding of a nonlinear equation, the equations in which the unknowns appear in the power or in the form of nonlinear functions. And we go for the conventional mathematics, abstract mathematics to solve this problem. But what I have tried to do here is to present this mathematical, very fundamental mathematical problem and its solution in an unconventional manner, in a manner in which if some researchers from multidiscipline come across with such equations, they do not have to go deep into the abstract mathematical concepts and the solution and the analysis of the problem, rather that they can have some kind of visualization tool through which they can not only solve the problem but can also analyze all the possible solutions and the situation in which they can have the solution. This talk will also associate mathematics in terms of aesthetics also. So I would rather be not be take up this topic in a traditional manner. The motivation of this talk comes from the fact that most of the relationship in the nature, they are non-linearly coherently. They have inherited aspects of when the cause is not in direct proportion with the effect. Then we come across with a nonlinear equation of this form, in which we can have either one unknown or several unknowns, and the unknowns either appear in the powers or in terms of the nonlinear functions. For example, the basic functions like exponentials, the trigonometric, and the logarithmic, etc. So from this property that there exists nonlinearity in nature everywhere, we have applications of having this mathematical problem in physics, chemistry, biology, information technology, and engineering. Usually we go for, first of all, we try to go for the direct techniques through which we can have the solution of this equation, which is also called as root, and we call this problem a root finding problem. But there are most of the time there happens when the equation has powers more than 4, that we say that it is above a quartic equation, or it involves nonlinear functions that cannot be handled in a direct manner to give the solution. We can go for the graphical techniques and indirect ways to have the estimates, but we cannot come across with the good, reliable solution in this manner. So what we do is that we go for some iterative methods. What are the iterative methods? They start with some raw guess of the root or the solution, and we work it out repeatedly, and such that we come at a situation when the approximate solution is according to our desired needs. The most widely used method in these cases, the iterative method, is the Newton-Raphson method. Most of you will be familiar with this one, as it is the first method that we take up, which is also good among all the classical methods to solve the root finding problem. But the demerits of this Newton method is that it is highly sensitive to the choice of the initial guess, that is the raw guess that we take to start the iterative method. So we need special analysis to identify the choices of initial guess for which we can have the approximate root, or for which the method goes to the workouts and goes to that approximate root. Recently, by going into the classical technique or the abstract method mathematics, rather we take up a visualization tool that is identified, which helps to analyze the working of iterative methods in root finding, and it is called basins of attraction, and this analysis is called dynamical analysis. Before going to the mathematical form of this iterative method and its dynamical analysis, we take up some problems from chemistry, from physics, from biology, from engineering, from information technology, and in which we will see that the equations that we have in these problems will be the one variable nonlinear equation or several variable nonlinear equation. The first application that we take is from chemistry and thermodynamics, which is van der Waals equation of state. We know that this equation it generalizes the ideal gas law based on the plausible reasons that real gases do not act ideally. Usually, in ideal gas, we treat gas molecules at point particles which interact with their containers but not with each other. That we say that they will not have an interaction with each other. So they neither take up space nor change kinetic energy during collision. So this equation explains the behavior of a real gas by taking in the ideal gas law two more parameters which take into consideration the interaction of the molecules among each other. We denote it with A1 and A2 specific. They are specific for each gas. So in order to determine the volume V of the gas in terms of the remaining parameters involved, we are required to solve the nonlinear equation. You see that this will become a cubic equation in terms of V. So if we are given the constants A1 and A2 and the values of N, P, and T, this equation will be a root finding problem. And since it is a cubic equation, it has three real roots. So by using some particular choices, for example, I have taken this equation for some particular choices of these constants and the other parameters involved, and it has three roots. One of them is a multiple root of multiplicity 2 that it appears twice, and the other is a simple zero that it appears once. The second application that I want to show to you is the Shockley diode equation and involvement in the electrical circuit. It is a very simple problem in physics that if we consider an electrical circuit consisting of a diode and a resistor, then by Kirchhoff voltage law, we know that when we apply the source voltage, it is equal to the sum of voltage drops across the diode represented by Vd and the resistor Vr. Now, if we want to find the voltage drops across the resistor, it comes from the very known Ohm's law, V is equal to IR. But for the voltage drop of the diode, we have to take an equation that gives the current voltage characteristics of a diode for an applied voltage. And it is known as Shockley diode wave equation. You can see right here that it is given like this, where I is the diode current and IS is the saturation current, VT is the thermal voltage. So the N is the emission, or we say that ideality constant, the quality factor, it is also called as a quality factor. So the terms associated with this diode are put into it, and upon simplification, when we substitute this voltage drop and the voltage drop from Ohm's law, we get this equation which is nonlinear, and see it involves a nonlinear function, logarithmic function here. In contrast to the previous equation, which was a polynomial equation, that is, it was an equation in which only the powers of the unknown was involved. In here, we see that the nonlinear function for the unknown I is involved in this case. For some given values of the parameters involved, we get a nonlinear equation, and the root of this equation has a simple real root, which is shown as 3.38, 9977, and so on. The next application is a trajectory of an electron in multi-pactor effect. A multi-pactor is a discharge phenomena that occurs in radio frequency components operating under vacuum condition. So an undesirable radio frequency breakdown, which may happen in the high power microwave devices working under vacuum condition, is known as multi-pactor. For example, it appears inside a parallel plate waveguide. So there exists a electric field with an electric potential which creates the electron movements between these two plates. If we want to find the trajectory of the electron in the air gap between these two parallel plates, then we come across with this equation where the involved symbols, the algebraic parameters that you see here, m and e are the mass and the charge of the electron. Then we have the periodic force sine omega t plus alpha. It is the radio frequency electric field between the plates. Y naught and V naught are the position and velocity of the electron at time t naught, and t is the time taken to achieve the trajectory. If you want to find this time, we consider the following case of the equation for some given values of the parameters involved, and we get again a nonlinear function. And for finding the time, we equate it to 0 to get the nonlinear equation, and this is again a root finding problem in terms of a trigonometric function as nonlinearity involved in this equation. The root of this equation is pi by 2. Next, we see another application from physics, which is Planck's radiation law. We consider the problem of Planck's radiation law, and it describes the spectral density of an electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature when there is no net flow of matter and energy between the body and its environment. And it is the wavelength variant of this law. So it involves lambda, which is the wavelength of radiation, c denotes the speed of light, k is the Boltzmann constant, T denotes the absolute temperature, h the Planck's constant, and assume that in this problem, let us assume that we want to find the maximum density of the energy psi of lambda. We know in mathematics, if we want to find the extreme values, we differentiate it with respect to the unknown variable lambda. So this is the derivative, first order derivative of this equation, and we equate it to 0 to get the extreme values. Now, we try to simplify this problem by taking a change of variable, t is equal to ch by lambda kt, to make it more representable. So this equation will take this form when equated to 0, and this is again a root finding problem. You see that now it has exponential function. So you see that you are seeing in the application that we get various kind of nonlinear function involving different type of nonlinear functions. The roots are 2 in here, and they are represented, you can see here. Then we have a fractional conversion in a chemical reactor. Fractional conversion of a reactant in an enclosed volume of tank is the ratio of the amount reacted to the amount fed. If no reactant is specified, then the fractional conversion referred to as limiting reaction. So if we model this problem, we will get another nonlinear equation, and here we have also natural log function involved in here, which is a kind of nonlinearity. Here x represent the fractional conversion of a species A in a chemical reactor. In fact, we have also, if we take another example of hydrogen-nitrogen chemical reactor, in a chemical reactor converting to ammonia, we get another polynomial equation of degree 4. So we can have different kind of equations, nonlinear equations in this application also. Next is also relevant to chemical engineering, the continuous state tank reactor. We consider an isothermal continuous state tank reactor. Components A and R are fed to the reactor at some rates. Then we have the volume schemes that develops in the reactor. We get another component B, then B is again fed with R, and then we get C, then D, and the final component is E. The problem can be analyzed in order to design simple feedback control system. In the analysis, we have to consider a following transfer function of the reactor, which you see it a kind of nonlinear equation. We analyze this equation for different values of Kc, which is the proportional controller, and we need to find those values of Kc for which this transfer function has negative real parts because the control system is stable for such values. If we choose in here kc is equal to 0, we get a nonlinear equation of polynomial equation of degree 4, and you say that all the roots of these equations are negative. So this value kc equal to 0 comes out to be a value for which the control system will remain stable. So in analyzing this problem, we will also come across with nonlinear equations. Next is an example from biology. It is a very interesting example that we consider the population growth model with immigration. We consider a population, we are analyzing the growth of population in a region or in a country at any time t with a fixed amount of immigration. Consider that case the birth rate of the individuals. This can also be considered in the biological labs where they find or analyze the growth of the bacteria on a petri dish. So we have this kind of differential equation, but you see if we find out the solution, it is a nonlinear function involving the exponential. Now we take a problem if we have initially 1,000 individuals and 3,000 individuals immigrate into the community in the first year. Also, let there be 1,365,000 people at the end of year 1 year, and they ask us the question that what is the growth, what is the birth rate of the individual in this year according to the given data. Then we put this data in this equation, and then we seek for the value of k for which this equation is satisfied. So this again goes to a root finding problem in finding the birth rate k. So the desired 0, if we find out, it comes out to be 0.055 and so on. Then we take another model that is from the ecosystem predator prey model in an environment. If we want to see the behavior of two species interacting with each other in a manner that one is prey and the other feeds on the prey, so it is called the predator. In this case, let us take an example of ladybugs as predators and aphids, which are small insects they consider as prey. So let x be the number of aphids eaten by a ladybug in some unit area. Then the number of aphids eaten by ladybugs per unit time, per unit area is called the predation rate. The predation rate usually depends on the prey density. So we have to see for those values of x for which the predation rate is equal to the growth rate of the aphids, so that the environment does not go in balance and the two species coexist. So the growth rate is considered through the Malthusian model, which says that it is directly proportional to the amount of aphids present at time t. Now, if we equate these two, predation rate and growth rate of the aphids, we get a nonlinear equation. You see a polynomial of degree n plus 1. And for the values of, if the predation is high, that is the ladybugs are eating at a higher rate, then n is large. Otherwise, we take a small values of n. So for appropriate values of n, we have to solve this equation to find those values of x for which the predation rate does not exceed the growth rate. Now we have another problem from engineering, civil engineering. We consider a beam positioning problem in a construction. We say we have a beam which has a length r meter, and it is leaning against the edge of a cubical box with sides of length 1 meter, such that one of its ends touches the wall and the other touches the floor. This I have made the figure of this. Now, what should be the distance along the floor from the base of the wall to the bottom of the beam? So we asked this question. So let us first set in the problem by taking the variables. Let y be the distance in meters along the beam from the floor to the edge of the box, and x be the distance in meter from the bottom of the box to the bottom of the beam. the solution is x plus 1, but we in here, if the x is unknown, so we want to find x. In this case, we will have two similar triangles, and if we take the ratio of base to hypotenuse of the two triangles, they must be equal. We equate these ratios and we get an equation which is non-linear, and for any r meter length of beam, we can solve this problem. Now, next problem is from climate change, the study that is going on, and it is very rapidly taken up. It is ocean acidification. Ocean acidification is the ongoing decrease in the pH of the Earth ocean caused by the uptake of carbon dioxide from the atmosphere. The main cause is, we know that it is the burning of the fossil fuels. So the global model, CO2 model, due to Bresnahan, taken in 2019, and its ocean chemistry, which finally leads to the numerical solution of a nonlinear fourth order polynomial in calculation of the pH of the ocean, from which we know how polluted it is. We get this fourth order polynomial equation. In this equation, the d's are actually in terms of the constant involved during this whole ocean chemistry. When CO2 is converted to carbonic acid, then carbonic acid, it dissociate into bicarbonate ions, and then it dissociates further into hydrogen ions, and therefore they contribute to the acidification. Also, additionally, the boron hydroxide in seawater dissociated to produce hydrogen ions. So all of these ocean chemistry, they when modeled, we get a degree 4 equation. So the solution is again a solution of a nonlinear algebraic equation. The next application, the previous application that we have taken, they give rise to a nonlinear equation in one variable only. But now we take the applications in which we get a system of nonlinear equation. For example, in information technology or global positioning system, in modern world, all our navigational devices, they work like this. The Google Maps, the military has applications for global positioning systems. So it is a network of orbiting satellites that send precise details of their position in space back to Earth. We know that there are 35 satellites now which are in orbits. They give signals. So the signals are obtained by GPS receivers such as navigation devices, and they are used to calculate the exact position, speed, and time at the user position. So this is how we, for having the user position, at least 4 satellites are needed to get it. So it is known that 4 satellites are required at least to find the user position in a GPS receiver. The system of nonlinear equation for finding the user position using 4 satellite is given as follows, that are known as pseudo-range equations. Here, the UIs, VIs, and WIs, they are the known locations of the 4 satellites that are orbiting, and USVS, WS is the required position of the user, and BS is actually the clock bias error, which usually comes up in here. You can see in this figure that this is the pseudo range, and in the clock error range is included. This BS can be measured using the difference between a receiver time and GPS time. So from the satellite constellation, a system of nonlinear equation is obtained for solving the user position. So we need to find also the nonlinear solution of the nonlinear equation, which involves several variables, several unknowns. Then there is a second example, which is electrical power system. In electrical engineering, different studies are carried out in steady state. Among them is known as the study of load flows, and the network equation, they are formulated in variety of forms. The formulation in the nodal admittance form, in case of when we take different nodes, this give rise to linear simultaneously algebraic equation in terms of node currents. However, in the power systems, power are known more than currents. Powers, the utilized powers are more well known. And then the resulting equation in terms of power, known as the load flow equation, becomes nonlinear and must be solved by iterative technique. So this is another phenomena in which we need, actually in designing the electrical power systems, we come across with these system of nonlinear equation, and we need to in the designing phase, we need to solve these equation to find to have the good design. So this is the figure that shows the nodal adjustment of these electrical power systems. Now we come to the iterative methods. So all these applications, so there is a great need to go for either the direct solutions or the indirect solution of the nonlinear equations or system of equations. So we need, if the direct solution is not admissible, we cannot apply an analytical method, then we go for an iterative technique. The most widely used and efficiently used is Newton-Raphson method, which was given in 1669. If we have real and complex, we go with a little mathematics and then we go back to the visualization tool. So there is not going to be more mathematics. For real complex valued function defined on interval AB of real line, if f satisfies the function, the nonlinear function involved is satisfies the certain assumption, it has to be sufficiently differentiable and the initial guess is close to the root. This is the one thing which bothers us, because the choice is very important. We work out this iterative method. We take an x naught, we come with another possible solution x1, then we take x1, we come with another solution x2, and so on. We generate a sequence, and if we have the proper initial assumptions, then this converges to the required solution of the nonlinear equation. Otherwise, there is most likely that it will diverge. Diverge means that we will not, this sequence will work out a solution which is not our required solution. It is not, it does not satisfy the given equation fx equal to 0. So it is kind of functional iteration repeatedly for values given x and we come to another value and so on until we have to set a criteria where we have to stop. So we see that how much accuracy we need and we stop according to that. Otherwise, it is an infinite process. And similarly, Newton method for systems can be extended when we have not one equation, but we have many equations. So this capital F will have many component functions. Suppose F1 to Fn, that is, we are going to have m nonlinear equation. In such case, this Newton method is converted into this vector matrix form. We take a vector as an initial guess. We calculate the value of this vector f at this given given vector x, and then the derivative in this case is not the rate of change, it is simple rate of change. It is the matrix which have derivatives of f with respect to all the unknowns. It is usually called as Jacobian. So this is the classical way of handling the systems of nonlinear equation from Newton-Raphson method. Now, as we have said that Newton method is sensitive to the choice of initial guess, I show you an example. This was then application taken for the fractional conversion of chemical reactor, and it was a nonlinear equation. It had two roots. Now, if I work out Newton's from the Newton method, I take an initial guess 0.76, and this Newton, because it is very close, this initial guess you see is very close to the actual root. So this Newton methods works because initial gas is close enough and it is converging to the root. So after 3 iteration, we see that we have 9 to 10 decimal place of accuracy. But if I take the initial gas from a little far from root, for example, 0.575 is the root, and I take the initial gas as 0.1, then it diverges. For the second root, if I take the initial gas 1.0, although it is very close to the root, but the Newton methods does not work and it fails. So this example shows you that how the choice of initial gas affects the working of the Newton method. Now, what we do then in here, usually in the mathematics, in the deep mathematics, we go for another technique which is called interval Newton method, and then for the proper choice of initial gas and for such functions which have a lot of zeros. For example, I show you this function f, which has 51 zeros in 210. So I need proper choices of initial gas, otherwise things will not work out. Even if you use a software to solve this equation, you use the solve command of Maple, Mathematica, or MATLAB, you will see that it will not show you any solution. It says that the solution may have been lost. So what you are going to do for such situations is that we tend to find those intervals in which the roots are expected to lie, which is this procedure is also called as isolation of roots, in which we determine an interval for each root in which only one roots exist. So this we do with the interval Newton method. We actually work out Newton method with interval arithmetics. We take an interval as an initial guess, we work out the Newton method in interval arithmetics, and we take the intersection of that interval with the interval taken from the Newton method. And in this manner, if I apply this interval Newton method, there are many utilities in Maple, MATLAB. There are built-in libraries through which you can do, or you can develop your own, and you can get in this way. See, I have got 51 subintervals in which the roots are expected to lie, and if I take initial guesses from this interval, the Newton method is going to converge most likely. Now, but it is difficult. Even if you go with the programming languages, you develop the sheets, the Maple sheets or the MATLAB programs. They are very, very long, and they are hard to develop, and there are some drawbacks of interval Newton methods through which comes into way, and then it is again you have to find an alternative way to go for these isolation of roots. So the question is, if someone is not familiar with this deep mathematics, or if someone wants to adopt another way to search for the roots of such an equation which is not solvable through the software, the usual built-in commands, then what we do now? So we go with the dynamical analysis. Let us see a video how this dynamical analysis give you a visual picture of the roots involved and the choice of initial guesses that you can take and the region of convergence and divergence. But initially, when you will see this video, you will have just an aesthetic sense of seeing an art. So let us have a glimpse of this video. I'm sorry, it has been. So what you have seen is just gives you an artistic view of a visualization technique for analyzing the choice of initial guesses for work out the Newton method for solving a nonlinear equation. Uh, this is called dynamical analysis. That by dynamical analysis, we do not mean that what we are discussing something which is changing with time. It means that we are seeing the chaos and fractals that are produced when we give different options to work out an iterative method for solving nonlinear equations. So we go for the choices or some choices of initial guess, and we see what is the response of that iterative method and how it behaves. So formally, we say that if alpha is the root of a nonlinear equation, then all points, all the initial guesses or raw guesses that we take, denoted by x naught, whose iterates converge to alpha, they are called the basins of attraction. So they are basically the convergence regions of the choices of x naught for which the sequence of iterates converge to the root. They are very useful for identifying the region of convergence and divergence of the iterative methods by giving the set of initial guesses which converges more rapidly. We will also identify for which kind of initial guesses the iterative method is fast and for which kind of methods it is slow. How we do this is that we give two different techniques. The first technique, we take a square region AB cross CD. Actually, we take the problem in the complex plane. We take the initial guess as x plus iota y, where x comes from this interval AB and y comes from CD. Now, for every initial guess x naught, we assign a color according to the root to which the iterative method is converging. And for the divergence, let us take some other color. Let us say here we take dark blue color. We also choose a stopping criterion for convergence by taking a tolerance epsilon that we decide how many number of decimal places of accuracy we require. And we also set a limit on the maximum number of iteration that we need to iterate, because if the method is diverging, that it will infinitely loop, so we have to stop it somewhere. In the second technique, we take the same scale, we take the same setup, but in here we assign the color to each initial guess depending upon the number of iteration in which this method converges to any of the root of the equation. We are not taking into consideration here that which root it is converging. We just are taking that it is converging to some of the root of the equation under consideration. If method does not converges in a maximum number of iteration, we consider the method as divergent for that particular choice of initial guess, and we assign a color to this divergence. In this second technique, we assign it black color. We have used MATLAB software, but you can also use Maple. You can go with Mathematica to draw these basins of attractions with different available color maps. So now let me give you a glimpse of the programming. It is very simple. It is the simplest program that we can have. We take the function, nonlinear function, to whose roots we want to analyze, whose choices of initial guesses we want to take. Actually, we take the initial guesses for which the method converges, and automatically it defines the regions in which we will have the root. The two roots are also identified here. It is not always important to identify the roots in the programming. We can have different stopping criterions in which the information of the root is not necessary. Of course, we are going for the approximate solution in the case when we do not know the actual roots. So here there are two roots, then the maximum number of iteration we are taking as 30. This is the stopping criterion tolerance. We want to have the root to at least accurate to 5 decimal places. Then we discretize the given AB cross CD interval into some number of points. The more points we take, the better visual you will get. So this is the discretization. We get the grid, and then now we start taking the initial guesses in the form of complex numbers. If the real part there is only a real part, that is we all there is only the complex part is zero, then we also take into consideration the real initial guesses. Now we work out this Newton method, then we take the stopping criterion, we check the stopping criteria at each step, that whether it is achieved. If it is achieved, then we assign a color which is assigned according to the number of iteration it has taken to achieve this route. And then we plot it with a certain color map, and we set the axis labeling, and so on, so and so. Now, by doing this, this is what we have for the example that we have taken for the fractional conversion of breeder reactors, for which I have shown you that Newton method is very sensitive to the choice of initial gas, and it also shows the same here. It says that see, there is a small region. You say see the shades of red. The shades of red are deciding the choice of initial guesses for which the iterative method converges in some number of iteration. You say that here are hues of red. So each hue determines that how many iteration it has taken. You see here the color band. So this CS says you that no more than 10 nearly iterations have been taken to converge to the root when it converges. Otherwise, there is a wide region which is black, which shows that it is very sensitive to the choice of initial guess, and it diverges to most of the cases. So you see here that around 0.8 the choices are converging. Here you see around this 1 point something to 1.2 the choices are responding towards convergence. Now, this was the technique in which we have not taken into consideration the choice of initial guess is giving us which route. But if we take into consideration the routes also, that if it converges to one route, it gives another color hues, and it converges to the second route, it identifies that for these choices is converging to the second route. So here we have 0 to 1 shade is for the root 1, and 1 to 2 hues are for the root 2. So you see that this is the region of convergence for root 2, and this is region for root 1. This is not very clear in this picture, but if in MATLAB, if I open this figure for you, I will open it after it, then you can also see the data cursor. You take the data cursor, you just click at somewhere to see at which point it is converging to which, so you can see the range of the initial guesses. You can identify the range of the initial guesses for which this iterative method, Newton method, is converging. So the same analysis can be applied to the other variants of Newton method or the other iterative techniques that are used to solve the nonlinear equations. Now this is I have shown you a glimpse of the programming, but you can also do it online. You don't have to go into the programming. So if I go to this link, if I can please switch my screen. So I stop sharing and I go to another screen to show you how this online generator works. So I stop it and then I share again, but now I share the online link that I have shown you. So this is the online link, if you can see. So is it, do you see it? So see here, this is the online generator. I select the Newtonian fractal, and this is the same x cube minus 1, z cube minus 1, for which I have shown you the video. And I put the polynomial values here, the coefficient of x cube is 1, the coefficient of x square and x is 0, and the constant is -1. So I put it here. Then this is a relaxation parameter. Sometimes they involve a parameter in the Newton method together with the f by f dash term. So r is multiplied with that fraction to get some other impacts. This is called damped Newton method. So if you choose it 1, it will go back to the Newton method. So if I just set in here and I just click, it will generate this figure. See, if I change, I go to z x power 4 minus 1 or some other polynomial of different degree. So let me change this to polynomial of degree 4. Then you see this region is changed. So there are some JavaScripts available online through which you can analyze this region of convergence and divergence. So this is one of the thing. This was given by Bhavan Kalantri in 2009. In the early 2000s, this theory has been developed, and he tossed the term of polynomiograph. This is the basis of attraction attached with the polynomials, and he also filed even a patent for it known as polynomiograph software, and through which you can have the analysis as well as the animation of this basin of attraction. So I can show you some other links as well where you can have let me show you, please. Again, I stop sharing and I go back to my PowerPoint slide. So I go back. So let me show you some other references. So these are the references, the books in which the mathematics is taken in terms of the applications from physics. So you see the list. All these applications I have taken from these books. So it is good always to keep yourself connected with the interdisciplinary problems, the problems that arise in other fields in sciences and engineering that you can go to solve, and so you can learn the practical applicability of the abstract mathematics that you always go through. And then there is a link you see here. It is a course of Massachusetts Institute of Technology, the Massachusetts University. It is about MATLAB programming, and it also covers one of the section of basins of attraction. I show you this link also. So I show you this link again. So we have this link, yeah, here. So see, this is the link in which basins of attraction portion is covered. So you can, if you want to learn more about this, you can learn from here. Moreover, we have discussed in here only the case of the one variable equation. So the basin of attraction for the several variable equations, they have also discussed it here. They have the code, they have discussed the code also here. So if you want to analyze the root of the system of nonlinear equation through this visualization tool, you can also go through this programming, and they have shown this picture here that is for a system of two nonlinear equations in two unknowns x and y. Also, there is one more link that I want to show you about this. Is it's about polynomiography. If I show you again, so this is a link in which you can see many aesthetic pictures of this technique when applied to different type of polynomials, and this is the link that was generated by Bhaman Kalantri, and he also gave in here. See, he also give in here some highlights. See, there are images, and there is also link to the demo software. I'm sorry, it had collapsed. the demo software polynomial graph that he identified. So this is all about this visualization tool, and I have tried my best to show you mathematics in visual manner. So in which those who are not pure mathematicians, they can also use this technique to solve a mathematical problem of nonlinear equations. And even the nonlinear equation, they also arise in ordinary differential equation. In the case of partial differential equation, when you go to finite difference methods and you come across with, again, nonlinear system of equations. So if you are even solving PDEs and ODEs through finite different techniques, and you come across with nonlinear system of equation, you also can utilize this technique to study the solution of those equations also. So thank you very much for your attention, please. So I take this back to Dr. Norma. If there are questions or comments that we can take.
Thank you very much, Dr. Fiza. Very privileged talk. I learned a lot from your talk. So many applications and the method on the numerical method based on the iterative manner. So now we have a question. All right. Okay, I have so many questions actually. All right. The first question, okay, I posed through the top chat, okay, the top chat at the YouTube, right? You are showing me too many, okay, method, too many application. So now, can you guide me how to meet the novelty for the traditional iterative method, for example, Newton just now, okay, of the numerical analysis. Okay, for example, if I have a PhD student, master student, okay, I want to enhance the traditional iterative method. Do you have any ideas, okay, to help me?
This in this talk you have seen there are two things. One is that the methods that are already known. So you want to go deep into the deep analysis. You want to have more and more information through to increase the applicability of that available method. This is one thing. So you go for all the different techniques. Like in this talk, we have gone to the analysis through a visual tool. So now we get deep inside into Newton method, and we see the working of this method. The second way is to propose another method which is good as compared to Newton method, because we see that in Newton method there are demerits. There is one demerit that we have discussed. We have discussed that the choice, it is sensitive to the choice of initial guess, but we know that there is another demerit. It is the presence of the first order derivative. So now when you have seen in one of the example that I have taken an initial guess and it fails. It fails means that it is not giving any result. If it gives a result which is far from root, then it is okay. We go for such an initial guess for which the method does converge. But if it is not working at all, you get an initial guess in the intermediate iterations, you come across with such a value where the derivative is 0, then the method fails. So you go for the methods that do not involve derivatives. This is one way. You can replace the derivative. For example, you go for the Stephenson method, in which the derivative is replaced with the differences, or you go for a more efficient method than the Newton method. For example, now there are many variants in the research that have been developed, which works better than the Newton method, which converges fast to the root. And if you want to remove all the demerits, you can go for the derivative free method. So this is how you either increase the novelty of the already available method, or you go for another new method that removes the demerits of that method.
All right. Okay, there is the basic question now is all right. Is how the weaknesses of the existing software in the market nowadays, right? And then how we can improve or how we can use the existing software, numerical software, for solving the non-linear equation.
So again, there are two things in the existing software. It is either the built-in libraries, the commands that are already available. So, for example, there are commands available for solving the method directly. But there are, if it's not working, then you go for, there are also built-in command now for the iterative classical methods. You apply the Newton method command and you go for the approximate solution. So there are some utilities available in almost all the softwares through which you can handle the weaknesses of that software. So it is not always important to go for a new software, but there are the things are improving day by day. You come across with another version of the software in which the libraries or the built-in commands are improved, in which there is involvement of the multi-precision also, which works faster than, which have compiler that are not very slow. So you can see which kind of software you want to take up. There are all available, and you take one software, you get into all of its features, and then you can remove the weaknesses.
All right. So I love to introduce Dr. Saima Akram. Okay, she wants to address a question. All right, the question is, what is the future of the iterative method?
Uh, Actually, up till now, we are working or researching in this area in a traditional manner. We have to adopt some innovative ways of not only developing new methods, but also developing the methods with respect to the practical problem. You take a practical problem, for example, I talk of the electrical power systems. Also, you go for the other problems of information technology, because it is now the area of IT. So you take the practical problems and you need to design the methods according to the need of those practical problems. It is, you don't have to follow the conventional path that go, you design an iterative methods and you try to apply to the practical problem. Rather go from the bottom, top down approach. Take the practical problem, take the problem from some industry of IT, from some chemical engineering maybe, and then you design such method which is useful for that, for solving that problem. So this is how that we can innovate new things in this area. Also, we need to go to the stability analysis more deeply into the already available problems, identify those which work for wider sort of problems, and so these are two ways. Either you go for the stability analysis of the previous method with reference to the practical applications, but I prefer that it is much better now to go for the practical problems and develop a method according to it.
All right. There is a from Prof. Tahi. I seen some fractal phenomena in your work. It is my perception right?
Yes, that's true. It involves fractals also. It involves the Julia sets, the boundary of the basin of attractions. They defines the Julia sets. Plus, you see some portion which are self-similar. So all so fractals and chiosol is already involved. It is actually the basins of attraction is a special class of fractal geometry. So you take one special case of fractal geometry and you apply to the iterative methods. You can go to the more general methods also. So for example, I've shown you the online fractal generator. I've chosen the Newtonian fractal from that available option. There are other options are also available. So this is one particular subset of that fractal geometry.
All right. Okay, Dr. Saima, okay, again, the question is, what is the major problem in solving system of nonlinear equation nowadays?
It's not about nowadays. It comes right from the advent of the iterative methods that are introduced. For example, first we introduced the Newton method for the systems. We see the Jacobian. The first derivative is transferred to the Jacobian in the system of nonlinear equation, and then you need to find the inverse of that matrix. So it is a very big problem to solve a new inverse every time. And if you are increasing the efficiency of the method, and you are defining new methods, and in which such Jacobians are involved, and you have to take so many inverses in there. So you have what we are researchers are doing nowadays. It's a very active area of research nowadays to solve the system of nonlinear equation. We have frozen derivatives. It means that frozen derivative means that we have to solve one derivative at a time, and we utilize the same derivative in the whole iterative method. We don't have to go, if there is a multi-step iterative method, we don't have to go to a new derivative at each step. And also to avoid the derivative maybe is a second area of research nowadays. So these are the major problems that if you know, Dr. Saima is one of my colleague, and she's also working in this area. Dr. Saima, if you know that there are no higher order good efficient methods for solving a system of nonlinear equations, still people are working on it, and they have not been able to go up to order seventh. They are stuck there, so they are working on it.
All right. So now, because you are doing modeling and then doing the simulation and then apply the software, implement on the okay, platform. So, how to meet the accurate solution? For example, just now you explained about trajectory of an electron and then radiation law and the growth of the population.
Hmm. No, we cannot talk about the exact solution in this case, because, of course, when we model, we have seen when we model these phenomena, we come across with the nonlinear equation of the form which are not solvable through the direct methods. So, what we do is that we need, we in the simulation case, we can go with the Simulink package of the MATLAB to see and analyze the model and see its behavior, how it's working. Or we go through these iterative techniques, more efficient iterative techniques too. We can have more accuracy at a faster rate, because Newton method is comparatively slow as if we talk of the new techniques. So uh, in the modeling, if we want to make the equation simple, then we have to ignore many factors. We know in that case, if we lose the useful information, then the solution will be of no use. So we cannot adopt such methodologies in the modeling in which we try to simplify the equation, because that will be of no use. But we go for some simulation, Simulink package or something, through which we can analyze it further.
All right. So, because of these problems, okay, can I suggest any controllability parameter? All right. For example, for beam, position, okay, problem that you addressed before. Okay, can we use this strategy to make it more precise, accurate, or considered as an approximation solution?
Yeah, we can. For example, we have taken a length r, so we can give an upper bound to the length that it cannot be no more than this long. So, in fact, in this way, we will be incorporating the optimization problem. So, this was the a very simple model that I have shown here. But we can incorporate other control parameters on the length of the beam, or the length of the wall, or the floor, what kind of floor we have. And then we go to the optimization problem, and then we can go for the numerical optimization techniques to solve that problem also. So we can combine this iterative methods with some numerical optimization techniques to solve the problem by involving some control parameters also.
All right. So since we have okay so many application nowadays, all right. So, may I know if there is a specific software to support the application above? All right, because
Hmm.
I'm really interested in the load of the electrical power system. Okay, for example, here, are you using any specific software licensing or open source software, right, to support application, for example, climate change, ocean acidation? Maybe you are using remote control, geoinformation system. I don't know. So,
Hmm.
as, explain here.
Yeah, Dr. Norma, I have not adopted, in particular, with reference to ocean acidification or load flow of electrical power circuits. I am new to it. I am just entering in designing the electrical power system, but I have seen some softwares like ANSYS that can analyze the particular geometry of the problem. So in designing phase, maybe we can use some kind of these engineering softwares to first see the design of the system and then go for its mathematical problem and its solutions. So I will explore, and maybe if I come across with some other softwares of these to handle these problems, I will share with you.
All right. So thank you very much. Okay, the last question from me. All right. Since we are handling the numerical simulation, we're handling the programming, all right, and then we are also request students to do a visualization based on the suggested model, right? Okay. Okay. For example, for myself, I ask the student to use a console mathematics for the early stage. Okay, how about you? Okay, how you handle the student-centered learning based on the programming, all right, check their simulation and the visualization of the model.
Hmm. Usually we try to have some interactive sessions. First of all, we because if I go with the Simulinks, I sometimes use in mathematical modeling course this Simulink package. So I go with the interactive session with them, and I explain them step wise, and then I ask them to repeat the same process. But of course, in online learning, you have to assign some activities to the students because fun activities, like for example, I have shown this link in which you do not have to go in the programming. You just say to them that if I give you this problem, just go through this online generating the software and give come up with some aesthetic picture with this kind of aesthetic sense. You have seen in the link of Bahman Kalantri, he has drawn many art pieces through this technique. So I think in the online learning, it is very important to attract the attention of the students, and this is only possible through the fun ways. I believe. I don't know about. I think it's going to be your experience as well, that you have to attach some activities like in which they feel good, they feel happy to spend their time.
All right. So I think this is the last question. All right. Any suggestion about the yield condition matrix rise while solving system of nonlinear equation?
In the
Yield
actually
condition.
we yeah, I know, we attach the air conditioning basically with the linear systems more rather than non-linear systems, because in the linear system we go for the solutions, if for the direct solution like Gauss elimination, Gauss Jordan. So we have to see that if it is a sparse matrix, it has more zeros, or it is ill conditioned, it is prone to the small changes, and it takes you far away from the solution. So you first measure the condition number to see that if it is a well conditioned system or ill conditioned system, and then you go for the pivoting techniques there. But in the system of nonlinear equations, because we are going with the iterative methods, and again we are choosing some sort of initial guess, and we are already analyzing that which kind of initial guesses are going to work, and also if there are errors, because there will be error involved, we can measure the errors as well. So we will have a study of the errors as well, so we can handle the solution reliability of the solution that we have after working out the iterative methods. So this is the possible way in case of nonlinear system of equations. But for the linear system, we go for pivoting strategies and other methods.
Oh. So thank you very much, Dr. Fiza. I really appreciate your contribution to OGC, Online Global Classroom, and the Faculty of Science. And I'm really, okay, uh, I'm appreciate what you're doing, all right? And I hope you have a good or breakthrough
Thank
in
you.
your research career, all right? And then without any delay, I would like to share screen here, okay, about the certificate that we are preparing to you. All right, before that, okay, let's go for the scan attendance for e-certificate and voting some question. Okay, most of the vote is said that numerical is one of a good solution. Right, so before, okay, we end this session, thank you very much. Okay, we provide the certificate, we will email to you, and then we hope that the collaboration will going, okay, ongoing. There are some activities, and this is the two, okay, for the first activities between UTM and Baharudin Zakaria, University Multan, Pakistan. All right. So thank you very much. All right, and then see you again.
Dr. Norma, thank you so much. I would like to thank the Vice Chancellor and Dean Faculty of Sciences, the Chairman of Department of Mathematics, and you especially. That I feel very happy to see how good you are working for the uplift of education, teaching, and research, in particular mathematics in the region. How you are joining hands with all of the universities of the South Asia region and all across the boundaries to to have possible collaborations and learning and sharing of knowledge. So I really appreciate your efforts, and I idealize you, that how actively and you work, mashallah. So thank you so much. Thank you so much for taking me in this online activity to make me a part of this very learning opportunity.
So thank you, Dr. Fiza. All right, I'll see you again. Right.
See you. See you.
Bye.
Bye. Bye.
Bye. All right.